Dear friends, welcome to the 6th lecture on module 3, where we are focusing environmental issues and management. In this lecture we are going to discuss about dispersion release models which are applicable to gaseous releases. This is a lecture under module 3 in the course of HSc in offshore and petroleum engineering at NPTEL IIT Madras. There are various dispersion models available in the literature which we have seen in the earlier lectures for chemical releases. Now let us talk about various dispersion models, the plume and puff models, which are useful for neutrally and positively buoyant gases. The plume and puff models are commonly used to model the vapor cloud dispersion, which were seen in detail in the last lectures also. The plume model describes the continuous emission of materials at height h above the ground level. The wind blowing direction is generally taken along the x axis, and the coordinate system for evaluating or estimating the dispersion model for a plume release is given in the figure here, where along the windward direction you will always see x is taken along the wind direction, y is taken normal to the wind direction, and z is measured along the altitude or height of the building. So the entire cloud dispersion which is formed by dispersion of the gas from the specific source, which can be a stack of a building, is actually a plume model which can be estimated from the equations which will be given to you in the next slide onwards. Now the plume release models or dispersion model gives you average gas concentration from the equation available in the screen now, where in this equation C function of x, y and z, where x, y and z are measured respectively along the wind direction, normal to the wind direction, and along the altitude of the height of the building respectively. So C x, y, z is actually the average concentration of the gas released using a plume dispersion model, which is given in the units of kg per cubic meter. H in this equation, what you see is the height of the releasing source, which is given in meters. X, y, z are nothing but the distances from the source in the downwind, crosswind and vertical directions respectively, all of them in meters because you have multipliers here. Q is the release strength, which is kg per second, which is the release strength of the gas of a specific concentration, and U used in this equation is nothing but the wind velocity in meter per second, whereas the sigma x and sigma y used in this equation in terms of sigma y and z, x, y and z are the dispersion coefficients in the x, y and z directions respectively. The plume release model can be calculated as different cases arise. For example, let us take case 1, where the ground level central line concentration can be given by this equation. The moment I say ground level, I will always associate z equals 0. I am talking about a specific point of release of concentration, therefore y is also 0. When I set in this equation y and z as 0, I will get C of x, which can be given by this equation. Case 2 can be ground, central line and release height, but of course h is taken as 0 in this case. So I can always find out the ground central line release of the plume model by given this equation as a concentration of the gas release. In both the cases of this above equation, x you can see is implicit in the dispersion coefficients automatically in sigma y and sigma z respectively. Now a question comes, what would be the value of maximum plume concentration? Maximum plume concentration always occurs at the release point. The release point can be tip of the stack of any chimney or any tower which is dispersing gas into the environment. For releases above ground, the maximum concentration occurs in the downward wind direction along the central line, which is taken as x axis for the whole calculation. The distance at which maximum ground level concentration would occur is given by a relationship, as you see from here. The maximum concentration C max is estimated by a relationship as you see here, whereas sigma z and sigma y are the dispersion coefficients available along z axis and y axis respectively. Alternatively, for instantaneous release we can also look at puff dispersion models. For continuous release we have already seen plume dispersion models. For instantaneous release one looks for a puff dispersion model. This describes instantaneous release of material. Example could be sudden release of chemical from a ruptured vessel. Consequences can be large vapor cloud is dispersed from the rupture point. Puff model is used to describe a plume. Alternatively, for example, effect of change of wind direction is a dynamic model of plumes. The average concentration for puff release is given by the equation shown here, where Cxyz is actually the concentration at different points of xyz measured respectively as shown in the previous slide. So, depends upon the instantaneous release of energy Q, whereas the sigma x, sigma y and sigma z, and of course h, x, y and z do carry the same conventional meaning as expressed in the last equation. There can be some certain specific cases, what we call special cases of puff modeling. Let us say case 1, the total integrated dose to be obtained at a ground level, that is where z is 0, is given by a dosage xy where 0, where it can take an energy of instantaneous release of the gas given by this expression. If one wants to find out the concentration on the ground exactly below the puff center, then it can be given by this equation. As you see here, y is also set to 0 in this case. If one is interested to find out the puff center on the ground where h is given to be 0, then one can find in this case a given equation. As you see here in all the equations, the sigma, z, y and x are actually given by the dispersion coefficient concentrations at various axes x, y, z respectively. The maximum puff concentration is always at the release height. The puff center is taken as the release height. The center of puff is located at x is equal to ut. On ground the maximum concentration always occurs directly below the puff center. Friends, there is a concept in dispersion release models what we call as isopleths. Isopleths measure the cloud boundary at fixed concentration. Isopleths actually represent lines of constant concentration. There are different steps available in the literature to compute or to plot isopleths. Step number 1, determine the concentrations along the center line at fixed point in the downwind direction. As you see here, this is my wind progressive direction. This becomes a center line of my dispersion model. There is a release point. Keep on plotting or finding out concentration at different points along the fixed line which is in the progressive direction of downwindward. Now at these points we know the concentrations available. Step number 2, find the off center distance to isopleth which is given by y at each point from the following equation. For example, at each point I want to find the off center distance to isopleth which is given by this equation, where in this equation Cx00t is a downwind ground center line concentration what you get from this particular point, and Cxy0t is an isopleth concentration at a specific value of x and y respectively. In step number 3, I plot the isopleths because I know the offset of the concentration at different points. Now I plot the isopleth offsets for both the directions at each point, then I connect the offset points as you see here and I draw isopleths. One major issue which is generally focused in estimation of release models is the dispersion coefficient sigma x, sigma y and sigma z respectively, which are very vital to estimate the gas release concentration, be it a instantaneous model or be it a continuous steady state release models. The dispersion coefficients are important to estimate the plume and puff model releases. They actually depend on stability class and downwind distances. Following are some of the steps to estimate the dispersion coefficients. One can identify the Pascal stability class by using meteorological data such as wind speed, heat radiation and cloud cover etc. Now you can see here for the surface wind speed varying from 2 meter per second to more than 6 meter per second, I have the Pascal stability class varying from A to that of F, where they are nomenclated as A, B, C, D, F, depends upon what would be the dispersion coefficient for different day incoming solar radiation and night cloud cover, or alternatively at any time during the heavy overcast. So, I divide the stability class into different nomenclature, not only depending upon the surface wind speed, but also depending upon whether it is day or night. Further, it is subdivided to slight, moderate and strong incoming solar radiation, whereas for the night cloud cover it can be taken as either more than 50% of the low clouds or less than 3/8 of the cloud formation. So, for different Pascal stability class, I can estimate the dispersion coefficients graphically using these figures seen here. In step number 2, classify the area, find out whether it is rural, urban or hilly terrain. Use the following figures to estimate the dispersion coefficients for relevant cases as applicable. Dispersion coefficients for plume release model for a rural sector is given below with a reference to Crowell and Lower in 2002. This is actually a log-log plot which talks about x axis the downward distance in kilometers and y axis has got two dispersion release coefficients sigma y and sigma z respectively. So, for different Pascal stability class varying from A, B, C, D, E, F in both the cases, you will see that if you know the downward wind distance whatever you want to calculate, if you know the stability class, project that to stability class and get the dispersion coefficient respectively. On the other hand, in this case as well, if you know the downward distance where you want to calculate the stability class, where you want to calculate the dispersion coefficient, whose stability class is known to you, then depending upon the downward distance in kilometer, draw a vertical line, intersect that line to the respective stability class lines and project it horizontally to get back your dispersion coefficient, maybe sigma y or sigma z respectively, which you need to use them in the release models in the equation shown in the few slides earlier. Similarly, one can also determine the dispersion coefficients using graphical estimates for plume release models for urban release centers. The earlier figure was given for rural release, this for urban release. Again, in this case you have got Pascal stability class plotted. You will obviously see the Pascal stability class in more of the cases remains linear in a log-log plot, but of course in all the cases earlier as well as in this case both rural and urban, you will see the values for the stability class A and B are much higher compared to the value for stability class E and F respectively, where AB refers to the wind speed, surface wind speed as low as 2 meter per second or varying from 2 to 3 meter per second, whereas E and F have a marginal variation which can vary from 2 to 5 meter per second and so on and so forth. One can also estimate the puff dispersion model dispersion coefficients for puff release model from the graphical estimates as you see here. Again, the plot shows x axis as distance downward, downwind side in kilometers, and the plot is available for all Pascal stability class varying from A to F respectively. In this case, you will see that sigma x is as same as sigma y because it is a puff release model, and sigma z varies along the altitude which is given by height of the release from the ground. Alternatively, friends, one can also estimate these coefficients from the equations given below for rural and urban conditions respectively. For a plume release model, you can always use these equations. If you know the stability class, if you know the rural or urban condition, you can use the respective equations for estimating the dispersion coefficients sigma y and sigma z, whereas in this the only variable which you have got to know is x, where x is the downward distance in meters measured from the point of release of the gaseous model. One can also estimate the dispersion coefficients from the equations for puff dispersion model. For puff dispersion model, you have the equations given for different stability class varying from A to F for rural conditions, whereas the variable here shows either sigma x or sigma y or sigma z, for x being the distance measured in meters in the downwind side measured from the release point. One can also look at the dense gas dispersion relationship. Gases having density higher than air are termed as denser gases. The dense gases released from the source initially slump towards the ground, subsequently they move upwards and in the windward direction in the downward side. Mixing mechanisms with air are completely different from neutrally buoyant releases. Bitter-McCall dense gas dispersion model is commonly used to estimate the consequences and the dispersion release models for these kind of dense gases. Bitter-McCall dense gas dispersion models have different steps to calculate this. Step number 1, characterize the initial buoyancy, which can be given by the equation Z0, where G is the action due to gravity in the equation, and rho 0 and rho A are density of release models in ambient air respectively. In step number 2, once you know the value of G naught, decide the release whether it is instantaneous or continuous. In this case, U is the wind velocity and x is the distance from the release point, whereas Rd is called as the duration of release. If the value estimated from equation 2 here in step number 2 exceeds 2.5, then you treat this as a continuous model, which can be taken as a plume model. If the F value computed from this equation is less than 0.6, then it remains instantaneous, which can be used as a puff model. If the value lies between 0.6 and 2.5, you can use both approaches of plume and puff model and see whichever gives you the maximum value, take that for your dispersion release. In step number 3, you calculate the characterization of the source dimension. For continuous release, which is the plume release model, the characteristic source dimension dc is given by this equation, where in this equation Q naught is the initial plume volume flux, which is given in volume per unit time, and U is the wind speed in length per time. For instantaneous release models like puff release model, the source characteristic dimension di is given by this equation, where V naught is the initial volume to be used in the calculation. In the next step, you can check the criteria. You already know the value of G naught obtained from step number 1. You know dc or da depending upon whether it is continuous release or instantaneous release. Therefore, for continuous release, you try to work out the checking criteria whether it satisfies the relationship that this equation, the value should remain greater than or equal to 0.15 for the model to be remain in a continuous release state. If the value is more than 0.2 for this equation substituted, then we can consider this model as an instantaneous release model. I can in this case use puff release models, whereas in this case I will use plume release models. Now, Bitter-McCall dimensional correlation is also available for gas dispersion. If the criteria is then satisfied as given in the previous slide, for example, in case of instantaneous release, this criteria should be satisfied. In the case of continuous release, this equation should be satisfied. For instantaneous release, this equation should be satisfied. If this criteria is satisfied, then the concentration ratio, which we call as Cm by C naught, is given by the following figures. Now, for different values of plume and puff models, as you see here, for different ratios of these constants of x over q naught u half root or g0 square qp u phi, you try to work out these values in x and y axis and try to know what would be the intersection point, and from that point you can always find out what would be the value of the concentration ratio Cm by C naught, whether it is an instantaneous release model or a continuous release model, where you can use either a plume release or a puff release respectively. Alternatively, one can also compute the concentration ratio Cm by C naught by the following equations as you see in the slide now. Similarly, one can use the dimension correlation for gas dispersion for the puff model. One can find out the concentration ratio Cm by C naught for the puff release models as you see from the slide now. One can now estimate the evaluation of a toxic effect cost by these kind of release models. Toxicity of the dispersed liquid or gas in the atmosphere is measured based on two parameters. The first parameter is the concentration of the dispersion. The second parameter is the duration of exposure. There are two standards by which one can always check whether these estimates are remaining within the conservative values. You can use either PEL estimates or TLV, time weighted average estimates, which are considered to be very conservative estimates for work exposure. There are 5 alternate methods other than these two to check whether these releases are within the permissible limits for toxic effect evaluation. Method 1 is based on emergency response planning, which is ERPG. This is actually formulated by American Industrial Hygiene Association. Depending upon the type of gas release or the chemical release, for every release available in the handbook, chemical engineering handbook, you have what is called ERPG level 1, level 2 and level 3 respectively. So, based on these ERPG guidelines available given by AIHA, one can always check what is the evaluation of the toxic effect on humankind. The second method is actually the guidelines proposed by the National Institute for Occupational Safety and Health, which is NIOSH. NIOSH actually recommends standards for immediately dangerous to life and health that explains the level of acceptable toxicity. Therefore, the level of toxicity acceptable to humankind is given by IDLH values alternatively instead of ERPG guidelines, as you see in the method 1. The third method is actually depending on the guidelines given by the National Research Council Canada, which is NRC. NRC actually recommends emergency exposure guidelines levels EEGL for different duration of exposure, varying from 1 hour EEGL value to that of 24 hours EEGL value. The next alternate method available to check toxicity permissibility on human mankind is given by method 4, which is OSHA's permissible exposure limit, what we call PEL. Occupational Safety and Health Administration, US Department of Labor, recommends permissible exposure limits of different toxic chemical on humankind. One can check whether they are within the limits given by PEL of that of OSHA, and one can say whether they are safe for the humankind or not. The fifth method is actually depending upon the EPA's toxic endpoint, which is based on the guidelines recommended by Environmental Protection Agency EPA of United States. EPA 6000 resolution 7/80 on 2007, which talks about the sediment toxicity identification evaluation guidelines, serves as a target value for checking the toxicity limits on human mankind. The sixth method is based on the guidelines recommended by American Conference of Governmental Industrial Hygienists, which is ACGIH in 1994. They give threshold limit values for chemical substances and physical agents for biological exposure indices, which is conducted in Cincinnati by the American Conference of Governmental Industrial Hygienists. So, they give guidelines depending on which one can check whether the toxicity limit of exposure on mankind is within the permissible limits as admissible by these standards. So, friends, in this lecture we discussed about different levels of gas release models for instantaneous and continuous release models, which can be a derived relationship for plume and puff models. We have seen different equations. We have also understood how to compute the dispersion release coefficients and how to find out the dispersion relation Cm by C naught for different states from the log curves as obtained. We also have found out what would be the different levels of acceptability of toxic limits as given by different standards in international measures. Thank you very much.